Okay, great. So I can throw this away. So welcome to Mission Control 4. This is the last mission control for the year. So, you know, we originally had one scheduled for next week, but we don't have any presenter. And actually, we went through all of the different disciplines that we wanted. So this is sort of like the business analytics mission control. Last week, we had the information security mission control. And before that, we had the games development control. So today, I'm going to talk about machine learning. But I'm not going to do it from a theoretical point of view because we actually have a module. I just got told yesterday that I'll be teaching that module. It's a 3000 level. It's a 3244 machine learning. So if you're interested in this topic from an algorithmic point of view, you should think about taking that next semester. But what we're going to do is cover how to do machine learning from a practical point of view. There's a very nice Python toolkit called scikit-learn, which hopefully you've had a chance to download, and a very famous machine learning data analytics competition site called Kaggle. Have any of you heard of Kaggle before? No? Okay. So actually, it's an international place where people put up data sets and competitions for machine learning and data analytics, and then you can participate in their competition for knowledge and sometimes for prize money and sometimes for hiring. So I'll talk about this a little bit more. Okay, so what we'll need to do today is first install scikit-learn. So we're going to do exactly that. So how you do it, hopefully you already have Python. Who here doesn't have Python installed on their laptops? Everyone? Okay, did you guys install scikit-learn already? You have any problem doing that? Okay, if you haven't done it, it's actually pretty easy to do if you have a Mac or Linux machine. Basically you use pip. If you have a Windows machine, I think you can do something very similar to that by doing that. Okay, so you can use pip to install scikit-learn. Okay, and it will have to build some of the other things that you need. So importantly, it needs NumPy and SciPy, which are two libraries that are for Python. Don't worry if you don't have these installed. You can install them in your leisure. Actually, when we use Kaggle, they actually have a VM deployed where you can actually use these online. So that's not a problem. Python also comes with this really nice feature that's common to a lot of newer languages called a notebook. So you can use IPython, which is a variant of Python that allow you to set up a notebook that has a web interface. You can enter Python commands on the web interface and have them executed. So we'll see that later on. Okay. But if you want to run it on your laptop, which of course you have your own cycles, your own CPU cycles to do, then I suggest that you do that. Okay, so you can follow these installation instructions later. Okay, so after the first half of the workshop from 2 to 3, if you haven't installed scikit-learn, you should probably do so. Okay, you can try it for other things. Like if you have Windows, then you can try to install scikit-learn using the instructions here. Okay? All right, so let's go ahead and go to, any questions so far? No? All right. Okay, so we're going to go through a little bit of slides just to get you started about what machine learning is, and then from there, it'll be probably a little easier to figure out what's going on. So let me see what I can find at. Okay, so basically I wanted to ask you a question to start with. What is machine learning? Okay, so I have a quiz here, right? Please select your answers. Is it A, memorizing something, B, learning facts through observation and exploring, or C, generalizing a concept from experience? Okay, so you can select more than one because it's a multiple choice, multiple select, sorry, not multiple choice. Okay. Do you think memorizing something counts as learning? Should it be counted as machine learning? No? No one? Okay. So 0 for that. Okay, I can't annotate with this, but anyways, okay. What about B, learning facts through observation and exploration? You have one brave soul who says yes. Anyone else? No? Okay. And C, generalizing a concept from experience. Do you think that's learning? 1, 2. Okay, in fact, all 3 of these are counted as learning. Okay, Singapore context, right? We do a lot of A, right? It's still counted as learning. MOE definitely, do, when they give you tests, they want you to remember what you've been taught. So yeah, all 3 of these count as learning, and they count as forms of learning for machines too. Okay, and actually, there are many different types of learning that you will hear about when you hear about machine learning, and it really depends on the type of feedback that's available for your use. Okay, so what do we mean by feedback? Let's say you go to your primary school or secondary school teacher, they give you something to do, they return back some exercise sheet or workbook, right? Then you get marked up, right? Some answers, how well you did. That's the type of feedback we need. Corrective feedback, right? So in supervised learning, right, the first bullet here, the correct answers are given for each example. So I ask you something like, what's 4 plus 4? You tell me 7, I tell you wrong. Okay? So for each problem that I give you a direct answer about whether it's right or wrong. Okay? Unsupervised learning means I don't tell you anything. I just give you a problem and you have to figure out the answer. Okay? So it sounds like a lot of what lecturers do, right? They tell you all of these things to memorize, and then when you go to the final, what the heck is this question? I've never learned how to do this question, right? So then you have to figure it out. Okay? What could be a task that is like unsupervised learning? Well, you may not be able to think of it, but one task that we commonly do in unsupervised learning is called clustering. Okay, so for example, I give you a whole bunch of items, like say marbles. Okay, I scatter them on the floor. They're of different colors, different sizes. I want you to make groups. Okay, how will you make groups? Well, I observe the space of the marbles on the floor and say, oh, there's some group of marbles on this side. They're really close to each other. Some other groups of here, which look like they're all red, etc. And I categorize the space into clusters. Okay, I don't know what the correct answers are. No one told me that this is supposed to be a cluster, but I can tell from the observations that it looks like there's some cluster of things over here, some cluster of things over there. Okay, so that's called unsupervised learning. Supervised learning is what we typically think of, right? Where you're given a question, you have to come up with an answer, and you're judged on whether that answer is correct. Okay, there's a third type that's been popular lately that's called reinforcement learning, which means instead of always giving you the right answer right away, we postpone the assessment and we tell you later. Okay, so for example, if I give you an exam question, okay, that has a final exam, okay, and I don't tell you what questions you got right or wrong, but I give you a final score, okay, you did 80 out of 100. That counts as reinforcement learning. Okay, because I don't tell you exactly what you got right or wrong, but I tell you over a basket of tasks whether you got it right or wrong. Okay, everyone with me? Okay, so what we're going to explore today is this type of learning called supervised learning. It's the most basic form, and we're going to show you how to do that in a very primitive fashion in the first half of the workshop, and we'll go over how to actually apply some of the machine learners in the second half. Okay, but first I want to tell you a story. Who knows what this picture is? Shout it out. AlphaGo. What is AlphaGo? Miss? Okay, it's an AI agent that plays Go, right? It knows how to play Go pretty well. And in fact, probably better than 99.9% of the world, right? More than that, actually. I don't think anyone in Singapore can beat this computer. Okay, so Lee Sedol was sitting on the right side here. He lost to this computer program that Google created. And it uses deep learning techniques. We're not going to cover deep learning today. Okay, but basically deep learning is also a type of learning program. Okay, what type of learning program is it? Is it a supervised learning, unsupervised learning, or reinforcement learning program? Okay, hands up. Supervised learning. I give you a problem, I tell you whether it's right or wrong. Right? You output something, you tell me whether it's right or wrong. No takers? Unsupervised learning. I never tell you whether you did the right thing or not. Okay? You just play the game and hopefully you do a good job. Okay? Good, we have one volunteer. What about the last one? Reinforcement learning. I occasionally tell you that you did a good job or not. Okay, so actually the third one is right, reinforcement learning. Why is that? Because at the end of each game, you either win or you lose, right? So in fact, you know whether the whole sequence of moves that you do led to a win, okay? You don't know anything about individual moves, right? Because you move, okay, so what? I get some stones flipped or not, okay? But I don't know whether it's right or not, right? I only observe at the very end of the game whether I won or lost, right? So a lot of these game-playing AIs are what we call reinforcement learning problems, okay? We don't get feedback at the very end. You play a whole game of Western chess, you either win or lose or you draw, okay? And from that, you're supposed to decide whether it was good or not, okay? So how does this work? How does reinforcement learning work? Well, basically, you can think of it in a nutshell, okay? If I played a whole series of random moves, and at the end of the game I won, then something I did must have not been so terrible, right? So I'm gonna say all those moves that I did somehow were good moves. I don't know which moves were good, but I know overall they're pretty good, okay? So maybe I have some function or some way of mathematically telling me that certain of these moves were better than others. But basically I'm saying that, you know, that entire stretch of moves from beginning to end were good, right? And the opposite is true if I lost. Okay, so when Google created this AI engine, okay, you might have heard on the news, it played itself, right? It played itself. What did they do? They took the same program and they had it play both A and B, like your left hand and then your right hand and then your left hand and then your right hand, okay? And it observes, right? It says that, okay, my left hand played all these moves and it lost. The right hand played all these other moves and it won. So next time when I play, I want to play more like my right hand than my left hand. And I do this billions of times. And over time, I learn to associate some moves are not bad and some moves are pretty shitty, okay? And then at the end of the day, I have trained a learner that can differentiate good moves from bad moves, okay? So it's not exactly the same as supervised learning, right? Because here, I basically am correcting each step, right? It's like a grandmaster presided over my game, right? Just like if you went to Go School here, right? And you make a move and he says, you need to think about why you're placing that stone. It should be over here instead. That would be a supervised problem, right? Like you see maybe in those magazines, you know, like if you ever play those magazines that say, oh, here's an imaginary scenario for Go or Sudoku or any other, you know, game, bridge, whatever, okay, when they have in newspaper columns, okay, tell me what your next move is, right? And then the next week, they'll show you a solution. That is like a supervised learning program, okay? But what we're talking about for AlphaGo is a reinforcement learning, right? Because you don't get feedback until the very end of the game, okay? All right, so good. Now we know how to talk cognizantly about it. So at your next cocktail party, tell them, you know, AlphaGo was a reinforcement learning problem. What does that mean? It means that, you know, only at the end of the game, they know some moves were good, and over many, many, many thousands, millions of runs of this, AlphaGo improved, right? You know, you and I as Go players, if you ever play Go, you probably don't have a chance to play more than 100 or 1,000 games in your lifetime. That's not a problem for a computer, right? We can set it to billions of games, no problem. That's why it gets good, okay? So as I told you, even though that's a very interesting scenario, we're not going to adopt that for this class. We're going to talk about supervised learning, okay? Supervised learning is the process of induction. Okay, induction is making predictions about something unknown in the future based on something that we have seen in the past. Okay, so philosophers have been struggling with this for centuries. Okay, going back to Plato's time, but probably most succinctly captured by Bertrand Russell. Okay, he said, if asked to why we believe the sun will rise tomorrow, right, we shall naturally answer, well, it's risen every day. Why wouldn't it rise tomorrow? But if you think about it from a philosophical point of view, there's no basis for us to believe the sun will rise tomorrow, right? Why does the future have to look anything like the past, right? There's no particular reason. We just agree with what we know, and so we think it's going to be like that, right? Who's to say that Superman won't just come flying down to Block 71 right now? You never know, right? Who's to say that the future looks like the past? We don't know, okay? But because we don't know, we make the simplifying assumption, probably not very sound, but anyways, we're going to make it, okay, that the past is going to be like the future and vice versa, okay? So induction, all of machine learning, supervised machine learning, was all based on this assumption, right? That the past looks like the future and vice versa. This can come into certain consequences that we'll talk about later. Okay, for example, I give you a lecture on machine learning, and then when I test you, I give you an operating systems exam. Okay, then the past doesn't look anything like what you're asked to do, right? Certainly you'll fail, right? So if I teach you about machine learning and I give you an exam on machine learning, hopefully there's some correlation with the examples that I've trained you on that can help you with the test, okay? All right, so induction or inductive learning is really, really, really simple. Basically, we can think of it as learning from a set of examples, okay? And nowhere is this more clear than having a function, okay? I'm gonna learn a function f. It is a function of some variable y. Function of some variable x, okay? So I'm gonna learn this f of x. I'm gonna give an example, which is a pair of x and the output of the function f of x, okay? And I want you to learn what this function is. And you're not gonna get it completely right, but you're gonna try to find a good approximation to that. Let me give you an example of that. So for example, I might have observations of people's height, okay? So I'm gonna observe people, how tall they are, by putting them on a measuring scale or looking at from them afar. That's about 1.7 meters, he's about 1.8, she's about 1.5, etc. Okay? And I'm gonna give you a function to guess, okay? What is their weight in kilograms? Okay? I want you to learn that function, okay? How do we do it? Well, I could provide it with some of these, right? I give you a whole bunch of people's height, okay? And I tell you their weight, okay? And I want you to make a function that can learn this, right? So I give you a person's height, you predict their weight. Sir?
Is it possible to create like a polynomial function that can map an arbitrary number of x's to corresponding x?
Exactly. That's what we want to do. We want to learn this function. We can make a polynomial function out of this. That's exactly where we're going. So we want to find this hypothesis h. It's up to us to decide what that h is. Okay, and I think this gentleman here is thinking, okay, some type of regression would do, right? Because I have some data points. I can plot them on an xy plane, right? And then I'm going to draw some like line through it. And that's going to be my function. That's a perfect example of machine learning. It doesn't sound like machine learning, but it is, okay? Because we're doing exactly that. We're going from, this part, learning some facts through observations and generalizing a concept into y equals mx plus b, and then using that to predict something, right? That's exactly what we're doing, okay? So here's a function, right? Let's say x is, again, people's weights, heights, right? And y, f of x, the y-axis is people's weights, right? Okay, then I can draw a line through that. Okay. Sometimes we're not so lucky. We don't get such a smooth curve, right? Sometimes we have sensors. Let's say the scale is faulty or something, or I don't measure properly from a distance. Okay, then my observations are going to be a bit noisy, and I still have to correct for this. Okay, I still want to learn a model that's reasonable. But sometimes I think, okay, my sensors are spot on. They got the height and the weight correctly. I want that as a true part. Okay, sometimes I'm going to think, I got something, but it's a bit noisy. Like this bottom X here doesn't really fit with the trend, right? So maybe I'm going to discard that. Those are hard problems. Those are called noise filtering. And if you talk to anyone who's in a data analytics or data scientist job, you have to do this all the time. Look at data, discard outliers that don't make sense, okay, and then figure out what the trend is from the rest. Okay, so we can do exactly what this gentleman, your name again? Varun? Okay, Varun suggested we, do some type of polynomial fitting, right? So we can fit a line. Does this look like a good line to fit? What about the rest of you? You guys say no. Well, what line seems to be a better line? You draw me a line with your hand, how it should look like? Anyone want to match these data points? A quadratic line, okay? Maybe a little bit like this one, right? That looks better, right? It seems to go through all the points except for one, right? So that's a better fit. There's a cost though, okay? This line is simpler to describe than this line. Why? Because a polynomial of quadratic means I have two parameters. Well, three actually, an intercept, x squared, and an x, right? The red line only requires two components. I need an intercept and a slope, right? So you can see if I choose a more powerful model, there's more things that I need to estimate, right? What about this line? It's a perfectly good line. It's even better than the last one, right? Would you say blue is better than green? What do you guys think? Yes? No? Hands up? Wow, okay, one person out of 6 is participating. Let's try that again. Yes? No? Fingers? Can I have hands instead of fingers? Hard to say, huh? Okay, it depends on what you think, right? If you think this X down here, that's, an outlier. That looks like something just went wrong. My scale is running out of batteries. I don't know. Okay, so I'm gonna discard that. Then I would say the green model works really well, right? But it's not to say the blue model is not good. If you think that's an accurate observation, the blue model is a much better fit than the red model or the green model, but it costs more, right? Why? Because the blue model is a third order polynomial. It's cubic in it, right? In order for this jiggle to happen, right? So the more power you introduce into your model, let's call it a model for a second, okay? The more expressive it can capture, but at a cost. There are more parameters, right? So obviously we would prefer the simpler model when appropriate, okay? Because it takes less things to explain, right? I can fit a line instead of a polynomial to it, right? So this fits all of that, but what about this one? This one is just as good as the blue one, right? It hits all the same places, right? How come we didn't use this as a model? What's wrong with this picture? It's still a polynomial, right? Of some very high degree. Is it a good fit for this model? Are you kidding me, Min? No, of course not. Why? It's too complicated. There's nothing in the data that justifies such a jagged graph, right? So in machine learning, and you'll see this over and over again, you prefer simpler models. Why? Because they're easier to justify, and you tend to fit the model that fits the type of data that you have. Okay, if you have a lot of data, maybe you choose a more complex model because you have enough data to estimate the parameters of your model well. If you have very little data, then probably you cannot do something like that. Okay, you have to choose a model that's fitting the right amount of data. Okay, all good so far? So there's a theory, or better known as Occam's razor, right? Choose the simplest explanation, right? So that's what we do. We choose the simplest explanation, but from a data standpoint, because it's easy to estimate good parameters for any model. Okay, now up to now we've been looking at graphs where x is one thing, right? So I told you, I give you the height of someone, you estimate their weight. Now you guys are all probably thinking, okay, you can't possibly do that. I mean, importantly, I need to know whether the person is a guy or girl, because people are different, right? I need to know whether they're Caucasian or not. I need to know whether they just ate lunch, okay? All of those are parameters, okay? We can include them in our notion of what an x is, okay? So when I say x is usually capital X with this angle brackets, I mean a vector, okay? A vector of values, okay? That is, instead of learning from a single variable, we are going to learn a function based on many different inputs. Some of those inputs could be continuous value, like height. Some of them could be enumerated values, like has eaten lunch, hasn't eaten lunch, Caucasian, Asian, Indian, whatever, okay? This could be enumerated types, okay? Or it could be even textual information, okay? So for example, I want to know what you might want to buy next week because I'm Amazon, okay? So I'm gonna look through all of the items that you have looked at recently, try to look at all the words that are in those reviews and say, oh, other items with those same words are gonna be things you might wanna buy, okay? But for machine learning to work, we typically make words into numbers. So we're gonna map words into numbers. And we're gonna say, for example, feature 152x78, which stands for the word, I don't know, iPhone, okay, is either on or off for this user. Okay, if it's on, maybe they're more preferably going to buy an Android phone or an iPhone. If it's off, maybe they want to buy diapers and vitamins, I don't know, okay? So we're gonna map all of these things to a multi-dimensional X, okay? So from this type of standpoint, now you have a regression model as well, right? You have a regression model on many dimensions, right? You have lots of different dimensions, all different types of X's, okay? And then you want to learn a single output, whether it's yes or no, or some numeric variable like height or weight. Everyone with me so far? Okay? Great. So let's try this, for example, okay? Ad blocking. You see this all the time in browser extensions, right? So, if an ad is supposed to come up by JavaScript, maybe you don't want to see it, so you turn your ad blocker on. How does it work? How could we learn this from a machine? Well, let's take the case where you're concerning something like this one here. This is an advertisement. This is called what? A banner ad, right? You know what they look like. They're like all the page wide and a little bit thick. Okay? So we could look at this, right? We could say, I'm gonna look at the height and the width of a graphic. Okay? Of a graphic that's to be loaded. Let's say I know the dimensions. Okay? And what I want to do is block ads, right? And as a supervised learning task, I told you I'm gonna give you examples of this, right? So now I'm giving you not one X, but two, right? An X with two components, a height and a width, right? X1, X2, right? And I want to learn whether it is plus or minus. Plus, it's an advertisement, don't show it to me, or minus, it's not an advertisement, let it through. Okay, everyone comfortable with that? So you yourself could do this. You could say, okay, I'm gonna go through hundreds of web pages, look at all the images, and I'm gonna assign for each one, I'm gonna tell the system its height, its width, and I'm gonna label it 1 or 0, or -1, +1, or whatever you want, true or false. I'm gonna learn two classes, okay? So I have some examples here, right? On this screen. I've annotated like 20 of them, okay? So I get a new image in, okay, the question mark. Is that an ad or is it not? What do you guys think? Hands up. Ad? Okay, one brave volunteer. Two? Hands up. Not an ad. Okay, everyone thinks it's an ad who's actually participating. Okay, that's good. I'd probably guess it's an ad. Okay, how can we learn a model of this? Okay, one thing we can do is memorize all of these things, right? For every example, I'm going to memorize, okay, if the width is 680 and the height is 40 pixels, okay, it's an advertisement. So anytime I see an image of that exact dimension, I'm going to call it an ad. Okay, that's called memoization, right? We do this a lot in the Singapore context. If you don't exactly tell you what is the model answer, you get it wrong, even though semantically it might be right. You see all these, Facebook posts about fourth grade primary 4 exams, right? Okay, but in any case, let's say this is the image, right? We can do what's known as k nearest neighbors. This is in fact a legitimate learning algorithm. What it does is very simple. It memorizes all of the examples. Okay, so I have access to all of these pluses and minuses. Okay, and then I have one parameter called k. Tells me how many neighbors I should consult. Which neighbors? Well, the nearest ones. Okay, so if I use KNN with 1, it means I look at the instance that's closest to the question that I'm asking, right? So here it is, right? Here's my question over here. I want to find its nearest neighbor, that's this plus sign. And then I say, oh, it's closest to a plus. It's got to be an ad. Okay, block it. Okay, I can generalize this, right? I can say k nearest neighbors. So if I take k equals 3, for example, it helps to be odd, for example. Otherwise, you could have ties, right? So I take the 3 nearest neighbors. Here's a plus. Here's a minus. Here's another plus. 2 out of 3 says it's a plus. Therefore, it's an ad. Block it. Okay? So you understand how this works. Okay? So there are machine learners that do exactly this, memorize the whole data set, and they just spit out an answer. Oh, you're closest to this. That's what you're going to get. Okay, we're not going to go there yet, so I'm going to go back to Kaggle. Okay. So I'd like you to go to Kaggle now at this address, kaggle.com. Okay. This, as I told you, is a bit like a global machine learning data analytics competition framework. Okay. So you can see, for example, some of the active competitions, like, okay, surgeons want you to identify nerve segments in ultrasound, or State Farm, which is an insurance company in the US, would like you to spot distracted drivers from video frames. Or Expedia, which I was previously going to do, would like you to guess which hotel cluster you're going to book based on your previous what you previously looked at in a session. Okay? Facebook would like you to predict which location you're going to check in, given that you're at a certain X and Y coordinate. So we're going to do this one, okay? So it says here, if you do this well, you can get recommended for an internship or full-time job for Facebook, okay? Not a bad thing if you happen to be doing it for Orbital, right? To say after the end of the summer, oh yeah, I did so well on this that I was recommended to get a job at Facebook, okay? So here we go. Identify the correct place for check-in. Ever wonder what it's like to work at Facebook, right? So they're saying, okay, this is one way you can be recruited to work there, okay? What we're going to do is predict which place a person would like to check into, right? So we're going to have an artificial city. It's going to be a 10 kilometer by 10 kilometer square, and there's over 100,000 places you could check in. It's a little bit like Singapore, right? We're about that small. Just kidding. Okay, and then you can look at the data and download it, and then try to make a submission. Okay. So we're going to use this data set. Okay, so we're going to first get the data. You click on this. Okay, you can see this. Okay, it's a bit too big to download on a wireless connection. 100 megabytes, 500 megabytes, half a gig. So I tried to download this at home yesterday. It took me 3 hours. So I'm not going to torture you with this. Okay, so I actually have a very small version of this data set here. Okay, you can download it. Okay, by going on this link. This is in the doc. Okay, so we're going to open up what this looks like. I shouldn't have done that. Okay, so this is what it looks like, right? There's a row ID, okay, which problem it corresponds to, an instance, okay, an X and a Y coordinate. So these things here are X and Y coordinates, okay? An accuracy, that means how accurate the X and Y coordinate is. Because many people, when they check in on Facebook, they're using a wireless connection. The GPS is not precise, okay? And then a place ID. This is what you're trying to predict. This is a particular business that they checked into, okay? So your goal is, given these columns over here, the X, the Y, the accuracy, and the time, you're supposed to predict which place they checked into. So you're supposed to predict, let's say, this company ID. Okay? That's the idea of this competition. So you're given X and Y coordinates again, GPS accuracy, time, and place ID. Okay? Okay, so yeah, you can look through the data set. It's all here. And you can do some obvious things with it. So we're going to do that by looking at this, okay? So here's a visualization of some of the data provided by some of the contestants in this competition. And it does represent a little bit like what happens, okay, in real life, okay? So when you use your phone to check into a location, you know, your X and Y location are captured. The accuracy or the strength of the Wi-Fi or the GSM, what global positioning system, GPS coordinates is captured, sent to Facebook, and you check in their place. So they know the X, the Y, the time, and your accuracy, and you're provided, of course, with the location that you're checking into. But you need to figure this out, okay? So for example, you might have a bunch of people who checked into this yellow location over here, but because their GPS is not very good, it doesn't show you one spot, right? And as you know, let's say, for example, checking into NUS, you could be all over NUS and you can still check into NUS. So some of these are actually polygons, they're not point values, okay? All right, what do you think would work well for determining this type of information, right? What is the target business that you are going to check into? Say you're given X and Y coordinates, right? You're given accuracy and you're given a time interval, okay? In a synthetic city, 100,000 places, X and Y coordinates, okay? What do you think might be useful to do the prediction? I mean, let's take a look. Okay, we're given these pieces of information, X and Y, accuracy and time. And we're supposed to predict this one, right? Place ID. Which of these things are going to be the most helpful? X and Y, right? Do you agree with that? If you're at Changi Airport, you couldn't be possibly checking into NUS, right? You're just too far away. Hopefully your GPS is not that unstable, right? So your X and Y is going to be primarily your source of information. In fact, if you look at some of the other people's descriptions of this, we'll find that to be the case. Let's take a look. Okay, so on Kaggle, they have this nice thing where they have scripts. Okay, scripts are what other people have done to help you make competitions. Okay, so let's take a look at some of these. Okay, let's see, Python starter, for example. Let's see. There were some that were pretty good. See, which one was I looking at before? okay, so for the next couple of hours, you can also do this on your own, is to go through some of the scripts and take a look at what they've done. Okay, and I'll show you how to do this later, okay? But basically what they're doing is reading in some statistics, right? So they're looking at reading in the training data, and they're checking what it looks like. So we just saw something like this. Here's the X coordinate, the Y coordinate, the time, and the place ID. Okay, and then they do some checks, right? So for example, I want to know how many training samples are there. I want to know the unique number of places that are in the data set. I want to know how many samples there are per place, right? So for example, as I told you, when I give supervised learning, I give you examples and I tell you the answer. Like I tell you, this X and Y, this accuracy, this time was used to check into this particular place, right? So if I have a lot of examples of checking into this particular place, probably I can guess that particular place better than other ones, right? So you can see what's going on. I have about, let's see, in the total data set, 29 million examples of people checking in. That's why the data is 0.5 gigs, right? There's over 100,000 unique places in this data set, and there are about 260 examples of people checking into a business on average, okay? And then we can take a look at some of those information, right? So topology of X and Y in some analysis, right? So people actually do this for fun, and you know, they do this to provide points to themselves when they're trying to be recruited by Facebook as well. So okay, so you can read some of the legends here. This is interesting. In this plot, each color represents a unique business place. So all of these are unique business places, right? Individual hexagons represent the last known GPS coordinates of a user who checked into these places. As you can see from the statistics above, variance in the GPS X and GPS Y samples are nearly similar. Okay, however, if we looked at the distribution associated with place ID, we sort of see that these coordinates are more scattered over X and Y, right? So it means overall the data set, you know, things are quite scattered over X and Y. But for a particular business, it seems that most people are scattered on the X-axis. Okay, so this is a particularity about the data set that some people have noticed, and that when you notice things, then you can exploit them, right? For example, if you notice this, you can say, if the Y value is such, I'm going to trust the Y value more than the X value. Because here, for example, this lime green business here, all of the check-ins are basically from this range of Y values, but they're all over the X value coordinates. Okay? Okay, so you can do things like this. Let's see. There's some other things that you can look at with time. So you can take a look at some of these visualizations. Okay, these are all, interestingly, notebooks that you can run yourself. So if you know Python, you can go and fork this notebook, which I'll try to do. I haven't done this before, so we'll see where it goes. Okay, and it will create an IPython or Jupyter notebook, okay, that will allow you to do this. So here are all the things that the person typed in, and we can run them, okay? In fact, you could download this script if you had the appropriate libraries, okay, and run it yourself, okay? So for example, I want to run this, I can click this little arrow icon here, or I can say, do this, right, Shift-Enter. You can do this in your browser too, okay, and run this. So I'm gonna Shift-Enter, and it's gonna say input data read, and then it's supposed to output something, okay? So it output a broken image, okay? And then I can run this one, all right? And I can run this, okay? All of these I'm gonna run, and you can see now it's trying to load in the entire data set, 0.5 gigs. Hopefully not on my budget, but the virtual machine over at Kaggle. So this gear is gonna be sitting there for quite a while. This is 0.5 gigs of data. And then it's gonna spit back me some statistics, which hopefully will be identical to the ones that you just saw earlier, okay? For exploration, like we're doing in this workshop, there's no point in using the whole data set. It's just too massive. Unless you're running a supercomputer with lots of GPUs and parallel processing, you probably wanna try with a small data set, okay? Which is why I've provisioned you with 1/100th of that grid. Okay, so if you go back to the train 01 CVS file, which I've put a download link to, you can see it's basically 1/100th of this set. It's all of the check-ins that go between 0.0 and 0.1 and 0.2 on both the X and Y axis. Okay, so all of this data is here. Okay. Okay. So you might think, okay, we know X and Y are really important. So if we restrict in this 10 by 10 kilometer virtual city, I'm going to restrict it to 100 by 100 meters, right? Which is basically what I've done by taking 100. What can I say about that? Well, maybe what I want to do, for example, is try something simple. Let's say, for example, for this data set, I want to know what is the most frequent check-in location, right? So I could do that by many different ways, okay? I'm going to do it on the command line here, okay? I'm going to cut the 6th field from the data, okay? By doing that, and I have now all the place IDs. There are, let's see how many of these, 3,900 place IDs, okay? So all of those are the place IDs from the data set that I have, okay? I just ran this command over here. It's a Linux command. Don't worry about it. You could do this in Microsoft Excel or any tabular sheet. Basically cut the last column off, right? And then you start to do some analysis here. Basically, this says cut the 6th field where the delimiter equals a comma from this file, and then pass it into a program called WC that just counts lines. Okay, so I want to know how many lines there are in a file like this. Okay. Now these are numeric values, so I can do simple things like, for example, sort it. Okay. Maybe I sort it as a number. Okay. So then I'll get something like this, right? So you can see now I have all the numbers sorted in order as I scroll up. Okay. And now I want to say, for example, which ones are the most common. So if you know Unix, you can also pipe that to another command. If you know pivot tables in Excel, you can do that in Excel. Okay, I want to know what are the unique items and how many times they were counted. So here you go. Here's a histogram of how many times a certain row happened. Okay? In this table. Okay, so here you can see, for example, this particular place only happened twice in this data set of 3,000 things. Okay, here we have another one, 380 something, 737 users out of the 3,901 check-ins were to this location in this 100 meter square. Okay, so now you get some idea. Maybe there are certain businesses that happen a lot. Okay. When I do this unique, right, I'm getting a list of unique values. I can also count how many are there. So even though the data set itself has over 100,000 unique places in this 100th of a data set, right? This 100 by 100 meter square part of Facebook City, okay? Only 100 and 191 businesses were here, okay? All right, let's try to think of this in terms of supervised classification, okay? Basically, I told you supervised classification looks a little bit like this, right? I'm given some x values, and I'm given some f of x, right? And those are examples. So can you tell me what x is for the Facebook problem? What's the values that I'm providing my learner with to make a decision? Yeah, those 4 things, okay? So my x is a capital X, is not a single value. It's a vector of 4 things, right? All numeric quantities, okay? What's my f of x? What am I trying to guess? The place ID, right? So in this particular small version of the problem, where we take in 100 by 100, I have 191 different answers. That's not so easy, right? If you went to a test and you got your MCQ form, and for the first question, there's 191 spaces to mark, you'd go crazy, right? But that's exactly what we're doing. We're trying to guess out of 191 places, which one place is where the user checked in. So this is not an easy problem. It's not an MCQ with 5 answers, right? It's an MCQ with 191 answers. Okay? Everyone understand what we're doing? So we're providing 4 integers, or 2 floats and 2 integers, okay? And we're trying to guess out of 191 places where it goes. Okay, so we're almost at the end of the first half, and we're going to talk about how to do this problem in more detail in the second half, okay? But for now, let's go and make a submission, shall we? So hopefully you've logged in, okay? You have a account on Kaggle, okay? And then we're going to go to the competition, right? We're going to go to Facebook, okay? And we're going to make a submission, okay? How do we make a submission? Well, it says here, your submission needs to be in CSV format. You can upload this as a zip file because the data is so massive. Even the zip is 100 megabytes, okay? And then you submit it up, okay? So obviously that's a little bit hard to do, right? I don't want to do that now. But we can use what other people have already done to make a submission, okay? So just so that you can familiarize yourself with how Kaggle works, okay? So we're going to go back to scripts, okay? And we're going to pick somebody who's done some work, and we're just going to plagiarize from them, okay? So in particular, we're going to use this grid plus classifier, okay? And I'm going to walk you through what this thing does, okay? So here you have in this sub.csv, if you download it, this is 200 rows, 200 million, sorry, no, 2.6 million rows of row IDs and where this person thought they checked in, okay? So this one says row ID 1, 0, with the X and Y accuracy and time coordinate. I think they checked into this business, and if that wasn't the right answer, I think they checked into this business. If I didn't think that was the right answer, then this business. Okay, for this particular competition, you're allowed to make 3 guesses. The first guess counts the most, so you get a whole credit if you get that right. If you make a second guess, the first one was wrong, the second one was right, you get half a credit. Okay, and the same for the third one, right? You get 1/3 credit. Okay, there's no penalty for the extra guesses. You can only increase your score. So you might as well guess 3 times. Okay? So what we can do is cheat, right? We're going to click this button, right? Submit to Facebook predicting check-in. So you can go ahead and do that. I'm going to do that now. It's going. Okay? And without knowing what this algorithm does, I'm going to send whatever this person did, all of their submission files, to Kaggle and ask Kaggle to rank me. Okay, so we're going to wait for it for a while that's going on. Okay, so this person is on the leaderboard. He's not that far behind the top. And he says, my best submission is mainly based on this script, this LB score, which I'll talk about later. Of the current state of the script should be pretty bad, but changing some information like the parameters, like the size of the grid, some thresholds, you can get a fairly good result, okay? But of course, because the data set is so massive, it could take a long time to finish, okay? So we're gonna take a look at this after it goes through, okay? So let's see. They sent the submission into their system and they're gonna score it. And then you can see how well it does, okay? So in the back over here, you can see 0.58 is pretty competitive, right? I mean, the top teams, at least the top 6, 7, or 8, they're all 0.58 something. So if you can tune this particular script the right way, you're already on the top leaderboard, right? You can see actually he's here at number 3, okay? So that's not bad. If you can go to a potential recruiter who's hiring for data scientists, which is like, I don't know, 90K, 100K per year, and say, I did good on Kaggle. This is an international competition. How well did your data scientist do? And then you can say, okay, you should hire me, actually. I know what I'm talking about. Okay. So we're going to score the submission. Unfortunately, this submission doesn't do that well, but that's okay. We're just learning, all right? And so we'll see how well we place. Okay, so I'm somewhere on this leaderboard, somewhere in here. And then I think, oh, we'll just wait for it to finish. That will be the same as what was scored. Any questions so far? Okay, so we haven't touched the machine learning part, but I'm giving you some of the prerequisites. What is machine learning? How is it executed? What's the form of a supervised learning problem? Okay, and we've covered Kaggle, and hopefully in the next couple of hours, if you're interested, you should go through some of the scripts that are on the Kaggle website and ask me any questions you want. I will have not explored all of the scripts, but some of them are pretty nice. And it's nice to know, even if you don't want to install all of this on your own, you can, work through it on Kaggle.com yourself. Okay, so hopefully we'll get a result soon. Pop. And it's like the Windows progress bar. Almost done, right? And it's stuck there for 30 minutes. Okay, so we're ranked 577th, which is pretty bad considering where the scroll bar is. So we're all the way down here, okay? But, it's better than nothing, right? So this is how well this particular procedure does, okay? All right. So as the last part of this, I'm going to walk you through what that particular script does, so you can have some idea of what it was doing. Okay, so we just submitted this. We're going to take a look at how the script operates by looking at the code. Okay, this, as I said, you can download it. It's just a Python script. If you have the data downloaded and you have the libraries installed, you can run it. You'll get exactly the same output as is shown at the bottom here, right? This output. Okay, anyways, we should go through this so you get some understanding of what's going on. Okay, so basically there are some import statements here. We're going to import some libraries, NumPy, which is the numerical Python, Pandas, which is for data analysis. You'll see that very heavily used in all of these machine learning things. It just provides a lot of data analysis techniques. It doesn't actually do any learning. So the learning is coming from this scikit-learn module, which they already have. So if you install it, you'll also import from sklearn, okay? Okay, and there's two sub-procedures. We're going to learn about them in a while, but we're going to scroll down to the part where it's running. So this is the main part of the program. Basically, it says I'm going to load the data, and then I'm going to make a data frame using Pandas. So PD is the Panda library. Okay, you can learn more about it, but it's not helpful to actually look at the documentation until you try it. Okay, so you can read about it here if you need to. But basically, what we're doing is we're reading in the CSV file, right? And we're specifying some of the columns and what type they are. So the column that's called an X, I'm going to save it as a floating 32-point precision integer. Floating point number. Accuracy is a 16 precision integer, etc. And the place ID is an integer, right? And the first column is an index. In fact, it was the rolled ID. So it just has a running value from 0 all the way to the end of the data set. I'm going to read in the test data set the same way. And basically, I'm going to have these two objects. DF stands for data frame. Okay, so I have a data frame for the testing and a data frame for the training up here. Okay, and I'm going to create a sample submission file, which I'm going to overwrite later. Okay, I'm going to read that in if I want to. Okay, here's where I define the size of the grid. So basically, this particular person has chosen to take this 10 by 10 kilometer city and divide them up in chunks of 1 kilometer. Okay, And for each kilometer, he's going to run some type of analytics to try to find what are the check-ins. Okay, so he's going to call this prepare data module to transform the data frames into the appropriate thing. Okay, so you're going to do some pre-processing. We'll see about that later on. Okay, and then try to figure out some thresholds. Okay, it says here TH, which is threshold, is set to 500. Threshold on place IDs inside each cell. Only the place IDs with at least threshold number of occurrences inside each grid cell are considered. This is to avoid classes with very few samples and speed up computation. Okay, so that makes sense to us, right? So earlier when we were looking at this output, right, and you saw, you know, for example, when I sorted this, okay, that in fact there are lots of place IDs that were only checked into very few times, right? So like all of these up here, they're only checked into one time. Okay, so by using this threshold, I would say I only want to consider places that have checked in more than 100 times. Okay, so I discard pretty much all the other data. I'm filtering a lot of data out so that I can concentrate on the majority classes. Okay, that's what this person is doing. I've done it for 1/100th of the data set. Sorry, 1/10,000th of the data set, because I have 10, 100 by 100. Okay, he's done it for 10 by 10 or 1/100. So he's actually looking at fairly big numbers. Okay. Okay. And then I'm going to process this grid after the submission is cut up into parts. Okay. So we're going to look at this prepare data and this process grid, and then that will give us some understanding of how this process works. Okay. So I'm going to go back up, and we're going to look at the process, the prepare data. Okay, so basically what the prepare data is in a lot of engineering jobs, you need to do this. You need to take the data and represent it in a way that is going to be helpful for you to learn values off of. In particular, in this problem right now, you will see that there is this field called time, right? This particular block here. So this is a number, and some people have some guesses what it is on the forum. Okay, this turns out to be a minute when they checked in. Okay, so if you know this is a minute, we can try to convert this into a date time object where we can extract out more data. Okay, so actually they found this out. Okay, and I can do something like this. I'm going to take for each of the data, okay, the time value. This is the column time. Okay, take the value, okay, and I'm going to create new columns from that data. I'm going to treat it as a date timestamp, and I'm going to convert something into hour, into weekday, into day, into month, into year, and then I'm going to get rid of this timestamp. Okay, because I think days of the week, time of day, seconds, minutes, okay, not seconds, all of those are probably more telling than a sequential integer, right? If you think about Facebook, people usually check in at certain hours of the day, right? You check into NUS probably not at 2 a.m. in the morning, hopefully not, okay? Or maybe you're going out with your friends for supper at 2 a.m. That's more likely, right? So definitely knowing, for example, the time of day, the hour, for example, whether it's a weekday or not, like whether it's 1 through 5, Monday through 5, Friday is going to be helpful, okay? And maybe even the day or the month of the year. Maybe some things, check-ins are towards the end of the month or towards the beginning of the month or during certain times of the year, right? So for example, if there's a holiday season like Christmas, maybe you can see that type of check-in behavior, okay? So converting some of the information in your data set to another form is usually quite helpful. Okay, so that's what this person did in their training data. Okay, they did it for both the training data and the test data, and they computed this important column. This says creating a new column with grid cell ID. So there's an ID number from 1 to 100 that indicates which cell it is, okay? So they just basically took the whole map and assigned it a cell, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and next to the next kilometer, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they enumerated a linear ordering for all 1 by 1 kilometer blocks, okay? And what they're gonna do later on is when they use the learner is process each of those blocks individually, okay? Okay. So they did some normalization. That's important for some learners, that all the numeric values exist between a range of, let's say, 0 to 1. Okay, so we can do that. And then they return the data set. Okay, so at the end of the day, after this step, basically we have the same thing as what I showed you before, okay, but with a couple extra columns added in. So I'm going to run a script. Let's see whether this is going to work. Okay, and I'm going to get something like what I saw, okay? So I'm here looking at the training data. I've only taken the head part of it. There's, again, 3,000 rows in here. So now I have the X and the Y. I have the accuracy, but instead of the timestamp, I've cut it up into hour, weekday, month, and year. And the script also is supposed to produce a cell ID, which I didn't show you here, okay? So with that, this is the actual input that I'm going to send to the machine learner later on. Okay, so I'm going to run the machine learner here, and then it's going to output some values about what it predicted. But we'll cover this in the second half of the course at 7 o'clock. Okay, any questions so far? No? Okay, so what I'd like you to do is spend some time, if you'd like to work on this assignment, okay, to learn about machine learning, looking through the scripts for this particular problem, okay? So you can go back to Facebook 5, predicting check-ins, look at the scripts, okay? And go through some of the different types of things that they're doing. You can see mostly they're in R and Python. You can take a look at the ones in Python. If you're comfortable looking at R, you can look at the ones on R. Okay? So that's it for the first half. I hope you join me for the second half. And those of you who are here, of course, you're welcome to order food through me. Again, it's up to you what you want to eat. You can have McDonald's, Pizza Hut, whatever you want. We have the budget for that. So I just need to get information from you so that by 5 o'clock we can order the food. Okay, with that, we're going to close the broadcast.